Thank you for joining me today, where I'm going to be talking about optimizing AWS Lambda performance and cost for your serverless applications. My name's Julian Wood, and I'm a Senior Developer Advocate here at AWS Serverless. I work with builders and developers to help them understand how best to build serverless applications, as well as being their voices internally to make sure we're building the best serverless products and features. I've been using and talking about serverless for a number of years, helping the world fall in love with serverless, just as I have, and now I get to do this at AWS. Please feel free to contact me anytime with your serverless questions, whether you have questions from today or other general questions around serverless development. You can reach me via email or Twitter anytime. All of the slides from today will be available to you after the tech talk, and you will also be able to watch this tech talk as a recording later. So we're going to cover three things today: cold starts, memory and profiling, and some architecture and best practices. Before we get started, let's just review how Lambda works under the covers. Now, this is a 300 level tech talk, so this will just be a quick recap. Lambda is designed to run your code on demand in response to events. Now, if we look at the anatomy of a Lambda function, there are several different layers, going from the outermost ring. First, there is the Lambda compute substrate, the underlying compute for Lambda. These are actually, the real servers in serverless. Next, there is the Lambda service itself, and this manages the scheduling and organization of workloads across hundreds of thousands of customers. Now, both of these layers are completely invisible to you and are managed entirely by AWS. A little bit further up, there's the execution environment. This is separate for every version of a function, not shared between functions, customers, or AWS accounts. It's a secure micro VM where the code itself is run. Within each execution environment, there's a language runtime. Lambda provides a range of supported language runtimes, including Node.js, Python, Java, .NET Core, Go, and Ruby. But you can also bring your own runtime, and there are customers running PHP, Rust, C++, Erlang, Perl, COBOL, and many other language runtimes. Lambda is agnostic to your choice of runtime and has no inherent preference for one runtime over another. And finally, there is your function, the code you provide, either zipped up as a package or included as a container image with any dependencies that you may need. The execution environment and runtime is instantiated on demand for scale events, and the function is instantiated for every single request. In this case, everything inside the handler is considered part of the function, and everything outside the handler is considered an initialization call and runs along with the execution environment initialization. From these 5 layers, there are 4 where you can make decisions that impact performance, and everything I'll talk about today is focused on these layers. Now, it's worth mentioning from a performance perspective that the AWS Lambda team is continuously working to improve performance on all the layers, so you get the benefits of these improvements just automatically as we release those upgrades, and this is just part of using a managed serverless service. You're also now able to run your Lambda functions on ARM-based AWS Graviton 2 processors. These Graviton 2-based functions offer up to 35% better price performance over comparable x86-based functions. Functions that run on the Graviton 2 architecture are already 20% lower cost-wise compared to x86 functions, and it's due to this improved performance of how Graviton 2 works that functions can run faster, which leads to up to 34% better price performance. The AWS Graviton 2 processors are custom AWS silicon, and they're designed by a company we purchased called Annapurna Labs, and has got a 64-bit ARM Neoverse N1 cores. And with our vast experience in running cloud-native workloads at scale, we've been able to target specific optimizations in the chip itself, and Graviton is literally designed for the cloud. And by building our own custom processors, we can rapidly innovate and iterate on behalf of you, providing great performance with significant cost savings. When you build a new Lambda function or migrate an existing Lambda function over, you simply select an architecture within the function runtime settings, and whether this is either a zip-based function or a function packaged as a container image, and you select ARM64 as the architecture. Now, if you're migrating existing functions over, there are a number of factors you may need to consider. Interpreted and compiled bytecode languages, so these are things like Node.js or Python or Java bytecode, and many of these can run uninterrupted without modification on Graviton2. Compiled languages do need to be recompiled for ARM64, but this can be a process that isn't necessarily too complicated, and Lambda container images do need to be rebuilt for ARM. Most AWS tools and SDKs already support Graviton2 transparently, including the CLIs and various SDKs for the various languages. So, looking now into the function level, there are a few different elements to understand. The handler itself, which is the function that will be run upon an invocation, and there are parameters handed into the function. The event object, which is a JSON describing the event, causes the invocation. It's an array and can contain multiple events. There's also a context object, and this provides methods and contains metadata which allows you to interact with the runtime and the execution environment. You'll notice here in the code examples above the handler, these are the function's dependencies and configuration options and helper functions and so on, which you add as part of the function. And here's where the function might initialize maybe a database connection, for example, and all of this is static initialization, or what is called init code. Putting this all together for when an invocation occurs, this is the function lifecycle within the Lambda service. When a request arrives for the first invocation of your function, Lambda first downloads the code into the part of the compute substrate where your code will run, and that then starts a new execution environment which is sized based on your function memory allocation. It then instantiates your runtime and then runs your code. This environment is kept alive for some window of time, and this depends on your traffic patterns. When a function is first run, all of these things happen. This is what is commonly called a full cold start. If another request arrives, only the handler is then run again, and this is much faster, what's called a warm start. And the first two steps are optimized by AWS, where the last two steps come to be optimized by you when you're building your functions. If you want to start measuring performance in a systematic way throughout your serverless applications, one of the services that can really help to do this easily is AWS X-Ray. And there are a number of different ways to do this. In the Lambda console, you can check the active tracing box in the X-Ray panel. And then after you save the changes, the console adds permissions to your Lambda function to enable X-Ray integration. Secondly, you can also use the SDK, and then when your application makes calls to microservices or public HTTP APIs, you'll need the SDK. The SDK also allows you to make some custom annotations and record additional metadata by using the code example on the slide. There are SDK calls for both synchronous and asynchronous function invocations. Then, as data is collected, X-Ray provides a visualization for invocations as they move between AWS services, and this makes it much easier to identify areas for performance optimization. At a function level, you can use X-Ray to drill into the duration periods of an invocation. This example here shows an asynchronous Lambda request with a successful invocation and one downstream call to DynamoDB. Dwell time is the time that this asynchronous invocation is spent in the Lambda service queue, the internal queue. It shows the time for the first segment, and each segment to invoke the function is a separate segment. And then at the function level, it shows the init code, and that's the static initialization code that runs before the handler, and the time taken by other AWS services used, such as DynamoDB in this example. And this granularity is important for performance optimization and informs where you can start looking to make improvements. That's a brief overview of the Lambda service and the distributed tracing system X-Ray. In the rest of this tech talk, we're getting deeper into performance optimizations, and I'm going to cover three areas of performance. The first is latency. Here we consider the entire round-trip time, which is the overall user experience, and we'll go deeper into cold starts. Throughput is the total number of transactions processed, and cost, reducing overall spend on your application. So let's get into cold starts. If we peek under the covers of the Lambda service, there's a distinct difference between a cold start and a warm start of your function, as I spoke briefly about earlier. All requests come into the Lambda service via the Lambda API. The Lambda service first checks to see if there is a warm execution environment already available. If this is the case, it means the function has been invoked previously, fairly recently. When this happens, this is called a warm start because the execution environment is warm and ready. Next, Lambda invokes the handler and completes the invocation. So how is this different to a cold start? In a cold start, since there's no warm execution environment available, there are some additional steps needed. First, the Lambda service must find an available compute resource and then download the customer's code. It starts and prepares the execution environment and then runs the init code, that's the code outside of your handler. Finally, it invokes the handler and then completes the invocation. There are some important things to know about cold starts. First of all, cold starts affect less than 1% of all production workloads. And this is important since you'll often see cold starts more often in development, since you invoke the function less often. In production systems, where functions are usually invoked more frequently and your application ramps up, they are less common. We also optimize to make cold starts as rare as possible. But when cold starts do happen, the time taken varies from under 100 milliseconds to over 1 second. And there are a couple of things to keep in mind here that first of all, you can't target warm environments. There's no mechanism for doing this. There's no affinity for repeat requests or any concept of sticky sessions. This is all managed for you by the Lambda service. Now, some people in the community have developed some libraries for keeping functions warm by pinging them with CloudWatch events. And yeah, this is fine if you want to increase the likelihood of hitting a warm environment for infrequently used functions, but it's really not a guarantee. And it doesn't help really much with cold starts when functions are scaling up, or if an execution environment is load balanced to another availability zone. If you really need a guarantee of a warm environment, a better approach is to use provisioned concurrency, which I'll talk about a little bit later. So cold starts are caused by a number of events. Warm starts do not stick around forever. Warm environments do not stick around forever. We regularly reap them every few hours to keep the execution environments fresh. And also, if Lambda is running on resources that could encounter failures, then the warm environments will be removed. Now, on occasion, warm functions are also ignored in order to rebalance load across availability zones. Now, Lambda is a multi-AZ service where the load balancing is managed for you. Also, anytime you update your application code or change your function configuration, this causes the existing environments to be flushed, and the next invocation will be a cold start. And then finally, there's scaling up. The Lambda service scales up when there's more work to be done. Each time a new concurrent invocation is started, that execution environment is started afresh, and it will be a cold start. AWS optimizes for this part of the cold start, the setting up of the execution environment, but it's influenced by 4 factors. The first is the memory allocated to the function. You can choose typically between 128 meg and 10 gig. Typically, functions with more memory allocated are reaped less frequently. Second, the size of the function package impacts the time taken for the service to download the code. Larger packages are slower to download. Making your packages as small as possible can really help here. Next, how often the function is called influences how long it is kept warm. Remember, environments are reaped every few hours regardless, and load balancing across AZs still happens even if they are warm containers. But generally speaking, functions used more frequently will be hitting warm environments more often than those used less frequency. And finally, internal algorithms that are just part of how the Lambda service optimizes customer workloads are a big factor, and we make changes to these regularly to provide a better and faster experience. One major improvement I'd like to mention is the work we've done already to improve cold starts for Lambda functions running inside customer VPCs. Now, customers frequently run functions inside a VPC to access services like Amazon RDS, Elastic Cache, Elasticsearch, or even EC2 and ECS. using AWS Direct Connect, you can also connect to on-premises resources using Lambda with VPC connectivity. Now, towards the end of 2019, we made a major change to the way Lambda functions work with your VPC networks. When you configure your Lambda functions to connect to your own VPC, it creates an elastic network interface in your VPC and then does a cross-account attachment. Now, previously, the creation of this ENI happened during the invocation process, so it could add considerable time to the cold start. And it also consumed resources such as a number of IPs in your VPC subnets. So as your Lambda functions scale, you have to think about this and be mindful of IP address spaces in your subnets and reaching any kind of limits. But after these, the VPC improvements, this process changed considerably, with two noticeable impacts. The first is the dramatic reduction in cold starts, and the second is the more efficient usage of network resources thanks to the use of managed network resources. And as you can see in the example above, one entire invocation was reduced from nearly 15 seconds down to just under a second. So these networking changes have now been the default for all functions for 2 years. So you now no longer really need to be concerned about the impact of VPC connected functions for cold starts. So that's the execution environment portion of a cold start. Let's look now at the second component of a cold start, that caused by static initialization or the init part of your code outside the handler. The code that runs outside your handler is frequently used to import dependencies, set up configurations, maybe grab some secrets or something from parameter store, and maybe initialize some connections. And this is run before the Lambda function at the initial start of an execution environment. And we've run analyses on Lambda performance, and data shows the longest cause of delay before handler invocation comes from this init pre-handler code. In other words, the section that you have the most control of can also have the biggest impact on the duration of a cold start. And this part of the cold start also occurs when a new execution environment is run for the first time, and also when scaling up. In this portion of the cold start, it's entirely influenced by only a couple of things. First, the size of your function package in terms of imported libraries and dependencies and Lambda layers. And so it's really important to be efficient in importing only what you need. And next is the amount of code and the amount of initialization work. And the key thing to remember is that execution environments are reused. So this means that you can do some optimization here. If you find yourself with many objects and connections, it might pay to see if you can re-architect into smaller, more specialized functions. And sometimes this is a really good approach and general good architectural practice. Secondly, it's important to import only what you need. Trim down SDKs and other libraries to the specific bits required. Pre-handler code is great for establishing connections to downstream services like databases, but be then prepared to handle reconnections in further invocations. What you can also do is lazily load variables in the global scope in your init code. Don't load it if you don't need it, and clear out used variables so you don't run into a leftover state for subsequent invocations. Now, having said this, there are workloads where there's a limit to how much you can optimize any of these things. If you really need to completely eliminate the cold start problem, but still be able to use large libraries of code and lengthy static initializers, then provision concurrency is the solution. Provision concurrency works by pre-creating execution environments ahead of usage, and this is all the way up to running the init code. It's really easy to use. You only need to specify the capacity, in other words, for the number of environments, and then when you want to use them, when you want to use them. So you can set this up via the Lambda console in CloudFormation and AWS SAM, which is our serverless application model framework. Now, it's mostly useful for interactive workloads that are heavily latency sensitive, and this is reducing the time to run the function handler to double-digit milliseconds. And it offers greatly improved consistency all the way through the long tail of performance at the P95, P99, and P100 levels. So going back to our function lifecycle flow, this is what happens when those execution environments are pre-created. First, the function is configured to use provision concurrency. Next, Lambda finds the available compute resources for the capacity requested. It then downloads the customer code into all of these execution environments and starts and prepares the environments. And most importantly, it runs the init code. Now, what's interesting here is that if you consider both components of a cold starts, the creation of the execution environment and running the custom init code, both are addressed by using provision concurrency. Since the environment is prepared in advance of the function usage, you no longer need to be concerned by the time taken for your static initializers. After the execution environments are prepared with provision concurrency, every function invocation follows the path above. And you recognize this flow from the warm start earlier, so every invocation in provision concurrency is a warm start. Now, there are a few things to know when using provision concurrency. First, it reduces the start time to double-digit milliseconds, and you'll see this in the X-Ray reports if you use X-Ray for your tracing. Provision concurrency can only be configured on a published version or alias of a function. By the way, and not on the latest version of a function, so something to bear in mind. Some customers use very large capacities, so it's also important to know that provisioning ramps up at the rate of 500 per minute. And bear this in mind, if you need 5,000 execution environments pre-created, this will take 10 minutes. Beyond configuring the provision concurrency specific attributes, there's no actual change to your Lambda code or handler. Now, if your usage goes above the provisioned concurrency capacity, that's no problem. All of the requests over this number will use regular on-demand Lambda. Invocations in this manner follow the usual on-demand Lambda behavior. Now, regardless of how you configure provision concurrency, overall account concurrency limits per region and account still apply. And if you need high levels of concurrency, please open a support ticket so we can help you out. Now, provision concurrency is also supported in AWS tools like CloudFormation and SAM, and in partner tools like the Serverless framework and Datadog and Thundra, so it's really broadly supported in tools and services you might already be using. Now, in order to maintain availability and help with scaling, we provision more resources than you actually request. Now, you don't pay for these extra execution environments, but because they run init, you could consume other resources from your account, such as database connections or calls to other services. And if you are doing some logging in your initialization code, you will see the extra capacity. Now, to keep execution environments fresh, we still reap them regularly, but we'll pre-create execution environments behind the scenes. So you'll see inits in your logs every few hours without configuration changes or any other events. But this won't impact performance. You'll always maintain the total level of capacity you requested for the function, even if we are reaping and pre-creating them in the background. For on-demand Lambda, init code receives a CPU burst that is typically higher than when the function handler is run. Now, this is not the same in provision concurrency. We give less CPU burst to provision concurrency than on-demand during init, and so code may take longer to run. Setting up provision concurrency in the console is straightforward. Once you've published the function version alias, you navigate to that version and then to the provision concurrency panel. Here you can specify capacity. Once you then save the new setting, the status shows how much capacity is provisioned, bearing in mind the 500 functions per minute ramp up. Once it's completely provisioned, the status is updated. And then it's possible to assign provision concurrency capacities to different versions of the same function. And this is the process used to set a fixed or known amount of capacity to a given function version. If you don't know what capacity to set or you need some assistance in setting capacity, another option is application autoscaling. You can use this through the CLI or CloudFormation, but not directly in the Lambda console. You set a minimum capacity and maximum capacity together with a target utilization. The service then responds to changes in demand and scales your provision concurrency appropriately. Remember that the 500 execution environments per minute ramp-up limit still applies. So for extremely heavy loads, it pays to set the minimum capacity at a higher level to ensure you have enough capacity to meet the demand. The usage of provision concurrency configured this way can be monitored via CloudWatch metrics, where you can see how many environments are provisioned and the utilization level. The second topic for today's Tech Talk is memory usage and profiling. The most important lever you have available in a Lambda function is memory. Lambda exposes only a memory control. You can select between 128 meg and 10 gig for your function. But memory is more like power, because as you increase the memory, this proportionally increases the amount of CPU core and network capacity allocated to the function. And up to 10 gig of memory, you'll be allocated up to 6 virtual CPU cores. Now, many developers leave the memory set to the default 128 meg, and this is fine for very simple functions. But if your code is CPU, network, or memory bound, then changing the memory setting can dramatically improve performance overall. And in fact, it can even be cheaper. Let me show you. Here's an example of a CPU bound function. It computes a whole bunch of prime numbers up to a million. When allocated 128 meg, this takes 11.7 seconds. As we increase memory to 256 meg, the duration drops to 6.7 seconds. Then, when we use 512 meg, half a gigabyte of RAM, it's 3.194 seconds for the duration. And finally, at a gigabyte of RAM, it only takes 1.465 seconds. Now, while it's probably no surprise that it's faster, what might surprise you is that it costs about the same within 1,000th of 1 cent. So why is that? Well, because Lambda billing is based on GB seconds, you can find that more memory is sometimes cheaper if the overall invocation time is substantially less. Or at least the cost might be comparable, as in this example, but you're getting a huge improvement in time performance. So obviously running tests on every single function with different memory allocations is quite time consuming, but luckily there's an automated way to do this. AWS Lambda Power Tuning is an open source tool that can help you visualize and fine-tune the memory power configuration of Lambda functions. It's created by our own Alex Castelbanu, who now works at AWS, and it's a simple way to find the right balance of memory, speed, and cost in an automated way. The application itself uses an AWS step functions state machine to run multiple concurrent versions of your function at different memory allocations and measure how they perform. The input function runs in your AWS account, so it performs real HTTP calls, SDK calls, cold starts, etc. The state machine also supports cross-region invocations, and you can enable parallel invocations to generate results in just a few seconds. You can implement a CI/CD process around this to automatically run this analysis as you build new functions, and you can also now compare the value of two functions graphically. In addition to the GitHub repo here, you can also find this app in the Serverless application repository. Just search for Power Tuning, then click on Deploy. Now, it supports 3 optimization strategies: cost, speed, and balanced. The Power Tuning app only requires a few parameters to start. The Lambda ARN identifies the target function which this needs to run on, and then the power values specify the memory allocation amounts you actually want to test. Num sets the number of iterations, the number of times basically that the function will run at each level up to a maximum of 100. And a larger number here can help smooth out some of those averages. Then there is an optional static polo that will be used for every invocation. And there are many other input parameters to enable some optional features. If you want to test your function against all available memory ranges in 64 meg increments, specify all in the power values parameter. Now, by default, this application runs each test sequentially, and this ensures that if your function calls other resources, it creates a fair measurement of the invocation time. But alternatively, you can have all the tests run in parallel using the parallel invocation flag. Now, depending on how many iterations to set in the num parameter, you may find the invocations are throttled. Another optional parameter is strategy, and this can be set to cost, speed, or balanced, and the default value is cost. If you use cost, the state machine suggests the cheapest option, disregarding its performance, while if you use speed, the state machine suggests the fastest option, disregarding the cost. When using balanced, the state machine chooses a compromise between cost and speed according to the parameter balanced weight. And balanced weight is a linear weight between 0 and 1, 0 expressing the trade-off between cost and time. 0 is equivalent to the speed strategy, and 1 is equivalent to the cost strategy, and by default it's set bang in the middle at 0.5. Now the auto-optimize parameters tell the state machine to apply the optimal configuration at the end of the invocation. If you need to use an alias for your function, you can set it here as well. Now without these parameters, this test will run and not make any changes to your Lambda function or environment, but here you can use it, and that example I was talking about earlier about a CI/CD environment, here you can automatically power tune your Lambda functions. So once the process is run and the state machine is completed, you'll see the results as JSON output. The number here represents the recommended settings for the tested function based on the input strategy. And the visualization attribute shows an auto-generated URL. If you visit this, you'll be able to visualize and inspect average statistics about the cost and performance. Now, these stats aren't shared beyond your browser since all the data is encoded in the URL hash, which is only available client-side. So let me show you some of the visualizations that the Power Tuning app can create. In this example, the x-axis is megabytes of memory and the y-axis is invocation time. The blue line represents total invocation cost and the red line is invocation time. This shows that for the fastest invocation time, 3 GB of RAM was the optimal setting for this function. But the lowest cost options were both 1 GB and 1.5 GB. So depending on whether your cost was lowest or your speed was lowest, you could then set the RAM allocation for the function as needed. And as I mentioned, you can now compare the function speed and cost of two functions, and Power Tuner is able to compute costs separately for both x86 and ARM. Here you can see I have two speed and costs graphs plotted. The functions are running the same code, one on x86 and one using ARM. And we can see that for both these functions, 2 GB looks about the optimal cost of the function before the cost increases. And we can also then compare the time and speed between the two functions. In this example, the x86 version and the ARM version. And here we can see that the ARM function version in this example is 27% faster and 41% cheaper than the equivalent x86 version. So this function would be a great choice to move over to ARM Graviton 2. So Power Tuner is super helpful to be able to compare your real-life workloads to see if you can take advantage of the 34% price performance advantage of Graviton 2. Now, we've run Lambda Power Tuning tool on thousands of different functions, so I just wanted to share with you some real-life examples and visualizations. For a very simple function that runs quickly, without interaction with other services, you'll see this kind of graph. You can see at 128 meg of RAM, the invocation time is comparatively high, and adding memory always proportionally increases the cost of invocation in this case. But in this example, it may be worth considering 256 meg. And this can often be 3 to 5 times faster than 128 meg with only a small increase in cost. So it depends on your use case. For a CPU-bound long-running algorithm, it can look a little different. This function, for example, uses numpy for compute-intensive calculations. At the 128 meg level, invocation time 9.5 seconds, and this drops rapidly as memory is added. At 256 meg, the total time is under 5 seconds, and at 1 gig is just over 1 second. In this case, the overall cost is fairly stable as memory increases, but performance improves up to 1 order of magnitude, 9 seconds to 900 milliseconds for just 25% in cost. Here's another CPU-bound algorithm for calculating prime numbers. It's a very long-running algorithm taking up to 35 seconds. As memory is added, the speed increases, but the cost also decreases until 1.5 gig. On this graph, 1.5 gig is a great optimization since it improves both speed and cost. Now, when you see a result like this, it's worth checking the lower memory bound with more granularity to see if it's even better at 1.3 gig or 1.7 gig. This is the same test as the previous graph, but run at 64 meg memory intervals, so it increases the granularity of the result. When we increase power granularity, we see that we can keep reducing cost and increasing speed up to 1.8 gig, which is half a second faster than 1.5 gig for only 2% cost increase. Switching gears, here's a function that's network bound. The function is making one third-party HTTP call. In this case, increasing the memory has limited impact on invocation time, but it's certainly more expensive. And this shows more or less the same performance across different power configs. While 128 meg is always cheaper, sometimes it might be worth exploring up to 512 meg. It can be 18% faster, but 3 times more expensive, while 3 gig is 20% faster and 30 times more expensive. And so it really depends on the use case. Here's another network bound function that makes 3 DynamoDB queries. And until 512 meg, the cost decreases, and then the cost starts to increase at 1 gig. Now, performance gets much better at 3 gig. It's 60% faster, but 6 times more expensive. And so in this case, 512 meg is a good trade-off between cost and speed. In another network-bound function, downloading a 150 meg object from S3, there's a 30% increase in speed from 512 to 1 gig, although it's 50% more expensive. Then performance stable for a higher value of powers, so you're not seeing any additional benefit. But here we can do even better by changing one single line of code and using a multi-thread download. So with the multi-threaded download enabled, it's 45% faster and cheaper at 512 meg, which now becomes the cheapest. So even the fastest 3 gig, which is almost 4 times faster, is now more than 4 times cheaper than before, and roughly the same cost and 5 times faster than the 512 meg single threaded version. And this is just a one-line code change. So different types of functions yield different results in the Lambda Power Tuning tool, and the visualizations can help identify the best cost-speed trade-offs for your particular use case. You can often find that increasing the memory and therefore increasing the power can give you both a faster invocation at a lower cost. But it really depends on the profile of your function and if that function is memory bound, CPU bound, or network bound, so it's worth running the profiler to see your results. Once again, this is the URL where you can download this open source tool, but it's available via SAR and really gives you a data-driven approach to choosing memory for your Lambda functions. Okay, in the final section, let's discuss some architecture and best practices. First of all, simply avoid monolithic functions. These are functions that contain everything in your application. It's better to have one function per purpose and enable specialization, and there are some architectural benefits too as your applications develop. But the most immediate impact upfront is reducing the deployment package size and improving the size. Next, minify your code wherever possible to help you get the package size as small as possible. Also, remember to lazily initialize shared libraries and objects, especially if you have multiple functions per file, and optimizing your dependencies and imports, for example. So we ran some tests and compared the results. If you need to use the DynamoDB SDK, include that specific package instead of the entire AWS SDK, and this can be up to 125 milliseconds faster. Similarly, for X-Ray, adding -core to the package name parameter in required saved 5 milliseconds. And in a test with X-Ray, switching from the capture AWS to the capture AWS client method and provide the document client reference was 140 milliseconds faster. So in each case, being more specific meant the code references a smaller package and it's faster to initialize in the init step. Going back to lazy initialization, here's a Python example. First, we import the Boto3 module and then set 2 global variables for the S3 and DynamoDB clients. If getObjects is called, the code checks if the S3 client object is initialized. If not, then it initializes it. If getItems is called, the code checks if the DynamoDB client is already initialized. If not, then it initializes it. And this is instead of initializing both objects in the init process. Now, this can make the individual function calls more responsive if sharing global objects across multiple functions. However, as you can imagine, this would not be a better option if you used provisioned concurrency. Many customers have petabytes of databases and relational databases, so need to use Lambda functions to access that data. Now, one of the problems always with traditional databases is that they are connection-based and are typically used with a pool of servers with long periods of uptime. When you use Lambda, this can really scale up and can overwhelm the database with connection requests. Connections are just memory on database servers, so it can of course impact performance too. As Lambda functions are ephemeral, the style of connection to a database really isn't ideal. So RDS Proxy is a great solution to this problem. You simply point your Lambda code at the proxy instead of the database, and the proxy intelligently manages the database connections. It can also make your applications more resilient to database failures and helps improve your security posture thanks to some of the features bundled with this service. It's an easy to implement solution that can help match the way scalable compute works with traditional database architectures. When optimizing for performance and cost, it's a much better practice to externalize orchestration. Avoid having your Lambda functions waiting around for some process to finish. Use step functions to be the orchestrator for this kind of work, which also makes your applications more resilient. Think of Lambda as a service to transform data, not transport it. Rather use native service integrations or things like S3 Select to pull in only the data you need and try to filter out data from triggers before they even get to Lambda to avoid Lambda functions running and then doing no work, or just doing work that filters something out. Allocate memory correctly, as we've been through, to get the most performance for the best cost. Use Lambda destinations to send records of Lambda invocations to other services. And this allows you to more simply chain successful Lambda invocations for simple use cases, and also allows you to send more information about failures to other services. Lambda destinations is preferred over dead letter queues or DLQs, but you can also still use these if you do want to. Understand the retry policies for Lambda and other services. And this is where Lambda can retry on your behalf. And this is very powerful and also configurable, and it's worth understanding to know the implications for your workloads. Now, many HTTP or HTTPS agents create a new TCP connection for every new request. Now, to avoid the cost of establishing a new connection, you can reuse an existing connection. And you can use the SDKs with an environment variable to specify to reuse a connection, or you can set the keep alive property in your function code. And this is a useful little trick, and for example, it can reduce a typical DynamoDB operation from 30 milliseconds to 10 milliseconds. Using service integrations is a powerful way to build modern applications. However, each integration you add increases the latency, which can be a concern for a synchronous workload when a service calls Lambda or Lambda calls another service. It's best to move away from synchronous invocations and rather move to an asynchronous model where the caller doesn't need to wait for the invocation to finish. You can also use VTL with API Gateway for direct service integrations, and also the new Step Functions SDK feature, which is really awesome and allows you to run any SDK call from within a Step Functions task without having to run it in a Lambda function. Again, use Lambda to transform, not transport. And avoid Lambda functions calling other Lambda functions synchronously, which causes a long wait time, increasing the overall time and cost. Lambda also has three types of invocation models. Synchronous, the caller calls Lambda either directly or through a service like API Gateway. Here it's calling the /get/order URL, which is mapped to a Lambda function. This sends a request event to the Lambda function and waits for a response before returning it to the client. When you invoke a function asynchronously, either via a client call or an S3 change notification, or maybe a service like EventBridge sending an event, you don't wait for a response from the function code. Lambda places the event in an internal queue and returns a 200 success response without any additional information. A separate process then reads events from the queue and sends them to your function. There's no return path to the calling service. An event source mapping is a Lambda resource that reads items from a stream or queue in batches. Lambda manages the polar and reads the messages and sends them to the function for processing. So when comparing synchronous and asynchronous invocations, for synchronous, the caller waits for a response which may take some time. Chaining these to downstream resources can also slow down the entire process, which can also be difficult to change as it gets complex with all the chaining. You then also need to manage and pass the payload between the steps in the chain. Asynchronous is a very powerful way to build modern applications. The caller receives an acknowledgement immediately that the message has been received, which minimizes the cost as the function isn't waiting idle. Queuing can also act as a buffering mechanism where events can be placed quickly and you can control how fast they are then processed by downstream resources. And this can protect some of those downstream resources like relational databases from becoming overwhelmed. Also, as the service is decoupled, change is simpler as you can take the consuming function or service offline, and when it restarts it can pick up where it left off, and you also just pass transaction IDs rather than the full payload. So to summarize, I went through 3 aspects to look at for Lambda performance. Cold starts, how they're caused, and how you can improve them, also explaining how the new VPC networking behavior no longer impacts cold starts. How you can use provision concurrency to avoid cold starts completely when you need it, and this is generally for high-scale synchronous workloads. I looked at memory and profiling, how memory is the power lever for CPU and networking throughput as well. How to use Lambda Power Tuning to decide between cost and speed, including how to compare functions, which is helpful for migrating to ARM-based Graviton 2. And some architectural optimization best practices, including RDS Proxy and the power of asynchronous processing and service integrations. Also, for plenty more information, head over to serverlessland.com, and this is a great site with lots of resources, blogs, videos, workshops, and learning paths. It's really everything about serverless on AWS. Thank you. I really appreciate you taking the time to watch today and hope I was able to help you understand how you can manage Lambda from a performance and cost perspective and be able to do even more with serverless. My name is Julian Wood, and you can find me on Twitter at Julian_Wood.